So the complex spectral theorem says that if V is a complex inner product space, F is a linear operator on V, then V has an orthonormal basis consisting of eigenvectors of F if and only if F is normal. And if it has such a basis of eigenvectors, orthogonal basis of eigenvectors, then of course F is diagonal in that basis. So we're saying, when does F have a diagonal basis? For the real version of the spectral theorem, of course, the real things are always a little bit trickier. And the reason for that is because of the presence of these two-dimensional invariant subspaces. Not as nice as the guaranteed one-dimensional invariant subspaces. And so in order to set it up, we need two lemmas, first of which I talked about last time. So lemma 1. Suppose F is in a real inner product space and F is self-adjoint. So it'll turn out that this is the right condition, the stronger thing, not normal but self-adjoint for the real case. Of course, self-adjoint in the real case, think about it as being symmetric. The matrix is symmetric in the orthonormal basis. If I take an alpha and a beta real, and they satisfy the inequality alpha squared is less than 4 beta. So this is the inequality that comes from asking that the quadratic equation x squared plus alpha x plus beta has no solution, so it doesn't factor into two pieces. That's what we want. The statement is that then the operator version of that quadratic form, f squared plus alpha f plus beta I'd v, this is an operator on LV, and the conclusion of the theorem is that it's invertible. So the reason for this, again, is to say that the space that corresponds to it, this invariant space that's going to end up corresponding to this, it corresponds to something which doesn't have a solution or doesn't factor. Okay. So in other words, that if I think about this as a polynomial, alpha squared plus alpha x plus beta, I can be sure that this is greater than 0 under these conditions. And the reason for x real, so this is not part of the theorem, this is just an explanation before we start the proof. And the reason for this is that I can rewrite this polynomial as x plus alpha divided by 2 squared. Since it's a real thing squared, that's non-negative, plus beta minus alpha squared over 4, which is greater than 0 by the hypothesis here. So this is greater than 0. It's equal to that. And that's will drive what's going on. So let's do the proof of this. Let V be a vector in our inner product space, which is not 0. We're going to do something a little bit funny, which is that we're going to look at this operator f squared plus alpha f plus beta I'd v applied to our non-zero vector v. inner product with V. And our goal is to show that this inner product is always positive, and so it couldn't possibly be that this operator kills this vector. If this vector, if any vector was a non-zero vector was in its null space, I could choose that vector, and then I would get 0 here. 0 is orthogonal to everything, and so I would get 0 for that inner product. So we're trying to show that it's strictly positive. So the first thing we do is by linearity, break it up into 3 pieces. The inner product of f squared v with v plus alpha fvv plus beta vv. By self-adjointness, I can move one of the f's over here. And then I get that this is equal to f of v plus alpha f of vv plus beta norm of v squared. Now the Cauchy-Schwarz inequality tells me that f of vv, its absolute value is less than the norm of fv times the norm of v. So I can conclude that this guy here, star, is greater than or equal to the norm of fv, which is the first term, minus, because the worst that could happen is that it goes in opposite direction, absolute value of alpha times this quantity, f of v's norm times the norm of v, and then beta we still add because these are real. Okay. And this expression that it's greater than can be factored, well, it can be broken up into absolute value, or the norm of fv minus norm of alpha divided by 2, norm of v squared plus beta minus alpha squared over 4, norm of v. So these are all just real numbers. The first term here is a square of a real number, so it's non-negative, and the second term, by our hypothesis, is strictly positive, and so this whole thing is strictly positive. Because it's strictly positive, that means that for no non-zero v, does this operator applied to v equals 0. So we can conclude that this must be injective, and since we're talking about an operator, injective implies invertible. That's the first lemma. The second thing we're going to need is under the same condition of self-adjointness for an eigenvector to exist. Remember that we had a theorem that said every operator on a finite dimensional, non-zero, complex vector space has an eigenvalue. And the proof of that theorem was by factoring a polynomial that came from thinking about f0 of v, f of v, f squared of v, and so on, up to f to the dimension of the vector space applied to v. That was n plus 1 vectors in an n-dimensional space. If n is equal to the dimension, and so it was dependent, and then we wrote this expression forgot about the v and thought, oh, this is a polynomial, used a fundamental theorem of algebra to factor it, and then argued that since this was equal to 0, one of the composed linear operators had to be responsible for killing v. And in the real case, we got a mixture of linear factors like this and quadratic factors that look like this and satisfy this equation. So that's what's going to happen. For our second lemma. So lemma 2, let V be a real inner product space, F a linear operator on V, and F self-adjoint. Meaning F star equals F. Then F has an eigenvalue, and so an eigenvector as well. Really, it's the eigenvector that we want to use. So with the inner product, we can say when an eigenvector has to exist. So we're going to make the same kind of argument. We let n be the dimension of the vector space, and we consider a non-zero vector in that space. And this list v, f of v, and so on up to fn of v. It's a list of n plus 1 vectors, and so it's linearly dependent. And there exists a non-trivial expression for 0 a non-trivial expression for 0 means I can write sum from I equals 0. It has to start at 0 so that we have v in there. Otherwise, it would only be n and not n plus 1. But it ends with some coefficients. So there's some linear combination of these things which equals the 0 vector. And in this linear combination, not all the ai are 0. So just as we did in chapters 4 and 5, we can view this as a polynomial x to the I and as a polynomial it has a factorization, some constant which is not 0 times quadratic factors x squared plus alpha 1x plus beta 1 up to x squared plus alpha big M x plus beta big M. And then a bunch of linear factors, x minus lambda 1 up to x minus lambda m. And here C, which is not 0, the alpha j's, the beta j's, and the lambda j's are all real. And the other condition which comes from this factorization, the theorem in the polynomials chapter, is that this alpha j squared is always less than 4 beta j. So we only need to use a quadratic factor if there are no real roots of a quadratic equation. Right? There's no real roots up here, and so that's another way of saying that there are no real roots. When we apply this polynomial back to our operator, we get that the 0 vector is equal to a scalar constant, which is non-zero, times a product of, a product of a bunch of quadratic factors. Now we have f's, alpha 1 f plus beta 1 identity, f squared plus alpha 1 f plus alpha m big M f plus beta big M identity times the linear factors lambda 1 f minus lambda 1 times the identity up to f minus lambda little m times the identity. And that's all applied to v. And when I do that, I get 0. We started with a self-adjoint operator. So by the previous lemma, all of the quadratic factors are invertible. So none of them have a null space, which is non-zero. So it must be that one of the linear factors has a null space, and therefore that it has an eigenvalue corresponding to whatever the non-zero vector that makes one of these linear factors just kills. So with those two pieces of information, we can state the real spectral theorem and prove it. So let V be a real inner product space. And F be an operator on V. Then our V has an orthonormal basis of eigenvalues of F if and only if F is self-adjoint. And so what that means is that over both either a real or a complex, if I have a self-adjoint operator, it always has a basis, an orthonormal basis that makes it diagonal. Over the complex ones, I can weaken that assumption to be only normal. But for self-adjoint, we're always all right. So the proof has to go two ways. The first is the easy direction. Which is to say, suppose first that V has an orthonormal basis B of eigenvectors of F. Since when I apply F to any of these eigenvectors, I just get a scalar multiple. And I've written the basis that way. The matrix with respect to that basis of F is diagonal. And each entry is real. And it equals its conjugate transpose. On the other hand, the other direction, suppose F is self-adjoint. Then we need to use our two lemmas. And we'll do an induction on the dimension of V. So in the case dim V is 1, we have a self-adjoint matrix which contains a single entry. It's real because it's equal to its conjugate. An orthonormal basis is just any non-zero vector in this space. Okay, so we're okay. So now consider higher dimensional. It's greater than 1 and holds for smaller dimension. And the idea is that we want to take an eigenvector of F, guaranteed by the second lemma, normalize it so it has norm 1. So I want to take an eigenvector u of f, divide it by its norm to make it norm 1, and then look at its orthogonal complement. The span of that eigenvector orthogonal complement, that's going to be our lower dimensional space, and we can apply our induction hypothesis, but what we need to do is check that f restricted to this span is still self-adjoint, and that this span is invariant. By the lemma I just erased, f has an eigenvalue, lambda. And rescaling, if necessary, let's suppose the norm of this of u, its eigenvector, is 1. And let big U be the span of little u, this vector. So it's one-dimensional. And I can consider U perp, the orthogonal complement, which has dimension 1 less than the dimension of V. And suppose V is some vector in the orthogonal complement. Consider the inner product of U, my eigenvector, guaranteed by the second lemma, with f of V. By self-adjointness, that's equal to f applied to U, inner product with V. But that's just an eigenvector, so that's equal to lambda times uv. So this becomes lambda u, and I can pull the lambda out. And that's 0, because u and v are orthogonal. We assume that v was in the orthogonal complement of u. So f of v is also in the orthogonal complement of u. What does that mean? That means that U, orthogonal complement, the lower dimensional space that we'd like to use for our induction, is invariant under the action of f. When I apply f to it, I get something else which is still orthogonal to U. So let V and W now be both in the orthogonal complement of U. We want to check self-adjointness. So because U orthogonal complement is f invariant, it makes sense to say I could take f and restrict it to the orthogonal complement of U. I apply that to V and take the inner product with W. That's equal to f of v and w, because v was in the orthogonal complement already. By self-adjointness, that's v fw, and that's equal to v f restricted to the orthogonal complement of w, because w was already in the orthogonal complement. And that shows that this f restricted to u perp solves the adjoint equation, and so it is self-adjoint. And so by the induction hypothesis, we have an orthonormal basis of the orthogonal complement of U, consisting of eigenvectors of f restricted to the orthogonal complement of U. almost there. Since f restricted to the orthogonal complement applied to v is the same as f of v, if v was already in the orthogonal complement, eigenvalues and eigenvectors of the restriction of f are also. So in the previous case where we dealt with the situation, we didn't have the invariance, and that's why we had to do more work. So these are also eigenvalue, eigenvector pairs for f. So to this orthonormal basis given by induction, we just add the new vector u, which is normal. Which has norm 1 and is orthogonal to all the other vectors. And then we get our full orthonormal basis.